Hello and welcome to the first of our talks on thermodynamics, a huge topic in all of science, but a slightly narrower one for chemistry, but one that does loop a bunch of different ideas that we've learned this year, mostly recently, all together at the same time. We just have a couple of thermodynamics talks, then maybe a few on other topics, and then we're going to wrap up this year. So thermodynamics is generally the concept of how heat relates to energy, work, chemical processes. It's a rather expansive concept that can be related to all sorts of different things. Chemists tend to narrow down that focus a little bit, and engineers do too, and there's lots of different ways to kind of perceive this depending on the discipline that you're looking at. But for chemists, it's mostly, as it says here, an issue of predicting and understanding under what conditions a reaction is favorable. That term favorable used to be actually labeled as spontaneous, and that got a little bit confusing, I think, because, of course, in a typical use, spontaneous means that something can randomly occur. So I could carry around a cigarette lighter in my pocket, and a chemist might refer to that as a spontaneously combustible mixture, but that does not mean that I live in fear that it's going to explode in my pocket and blow my leg off. That the idea of spontaneous, as it was first used chemically, is simply that in the conditions in which it's placed, the reaction, once it's started, can proceed from reactants to products without the need of excess energy. So once you put in activation energy, once the reaction is started, it can proceed to the products without external assistance. So once started, and again, that usually involves activation energy of activation, the reaction can proceed to the right without extra help. And reactions that are not favorable, or in the old days non-spontaneous, or what I would just refer to as non-spon, those need constant inputs of energy in order to work. So they're not favorable. So imagine the idea of a combustion reaction. A combustion reaction is obviously heavily favorable. Once you add that spark, that activation energy, off it goes. You don't need to keep adding heat or anything to it. But something like photosynthesis does not work unless there's a constant input of sunlight. Plants can't perform photosynthesis without energy coming in. So that reaction is not favorable under conditions that do not involve that energy input from the sun. So that can become more nuanced, as we'll talk about, depending on things like temperature. So some reactions may be favorable at some temperatures, not others. So imagine something as simple, and we'll talk about this in a future talk, as ice. Ice melts favorably above 0 Celsius, but does not melt favorably below 0 Celsius. And the fact that there's a flipping point temperature-wise of 0 degrees Celsius gives a hint about equilibrium and how it may relate to this as well. So the reaction favors the products above 0 Celsius, but favors the reactants below 0 Celsius, and that kind of thing. So there are a lot of relations to other topics then. So electrochem, thermochemistry, as I just sort of indicated, of course, equilibrium. So we'll talk about that both conceptually and quantitatively. We're going to put some numbers to all this, as chemists often do. Some of the concepts briefly, and we'll talk about them a little bit more as we go into detail with each of some of the laws and mathematical formulas that we talk about and the topics to which they relate. But some general concepts here. For instance, a working battery is favorable. So that a battery that's producing voltage is moving to the products, and the volts are one of those products, and so that is favorable. Once the battery starts, it works. You don't need to keep adding energy. That would defeat the purpose of a battery if you need to add energy to help it keep working. Exothermic reactions also tend to be favorable. Now, please note that I'm talking about tend to be here. We're not talking about guaranteed to be. The concept that usually is shared is that exothermic reactions tend to promote favorability but do not guarantee it. So that exothermic reactions, not all of them, but most of them are favorable. Reactions that increase the amount of entropy, which we'll certainly talk more about, also tend to be but are not guaranteed to be favorable. And reactions that favor the products are favorable as well. So again, from an equilibrium sense, reactions that tend to move to the products with a K value larger than 1 tend to also produce favorability. Mathematically, quantitatively, we oftentimes refer to this in terms of what's called Gibbs free energy, named after Josiah Willard Gibbs. J.W. Gibbs was a professor of physics at Yale. I think he was one of the first, if not the first, PhD awarded in the United States in physics, and had a very, very illustrious career as an academic and actually as an administrator at Yale. And he came up with this idea of what he called available energy. So originally it was called available energy. So if a reaction or a process was working to the point where there was actually energy coming out of it that was available to do work or cause heat to do work, then it was available. So there was energy available to do more work or to change things. Once that concept really caught on and people realized how you could quantify it and apply it, it ended up being named in honor of Gibbs. And so Gibbs free energy, just G, or the change in Gibbs free energy as we go from reactants to products, delta G, is named for him. And so generally speaking, if delta G is negative for a reaction, that means that there is available energy. In other words, the reaction is sending energy out away from itself. So the reaction or process produces free energy. And that concept is sort of like a negative delta H being a reaction producing heat. So the reactants are losing energy they have stored up in them as they become the product. So there's a net loss of that available energy, and that means available energy is going out to the surroundings and is available to do work. A positive delta G is that the reaction requires energy to work. And so again, it would not work unless you add energy to make it work. There's not available energy. Available energy has to come from the surroundings into the system to help the system work. Just summarize this, we'll make it a really short introduction today. It's key that you maybe understand this then to relate these ideas. A negative delta G is then a reaction that is favorable or spontaneous, back in the old terms. And then a reaction with a positive delta G is non-favorable or unfavorable, and again, what I used to call just non-spontaneous. You may be thinking, if you're thinking ahead and this is how you think about things, what about a value of 0 for delta G? What does that mean, do you think? That means it's not really moving to the products, but it's not really moving to the reactants, and so the reaction is either not doing anything, or sometimes, and this works for not doing anything, but generally speaking, we're talking about some sort of relationship to equilibrium here, and we'll talk more about that in the coming days. So for now, just a quick introduction to thermodynamics. In the coming presentations, we'll talk a little bit about how this relates to each of the sort of big units that I mentioned earlier: thermochemistry, electrochemistry, and equilibrium. We'll go into each one of those. I'll probably do more than one each day. We'll look at the mathematical formulas and the concepts behind them, do some sample problems, and kind of move our way through our last big topic. All right, have yourselves a wonderful day. We'll talk to you later.